Seen what is your what is your humidity ratio or specific humidity. Now, this gives some sort of a measure of water vapor actually present in a sample of moist air. But it has been seen that this does not give us much information regarding the comfort feeling in a particular sample of air. Okay. So, for that we need to define certain other quantities. First, I would like to define dew point temperature, and then we will go to the other quantities. Dew point temperature, it is related to the process of condensation, and we are familiar with this process. That means that when the temperature is lowered, then in a particular sample of moist air at certain temperature we will find the presence of liquid water. Now, this liquid water, they are generally formed in the form of small droplets and on cold surfaces, and they are most commonly known as dew. So, that is why the temperature at which these liquid droplet appear, that temperature is known as dew point temperature. Thermodynamically, the process is something like this. If we have the TS diagram and this is the two phase zone. So, a constant pressure line is something like this. This is the constant pressure line, all right. This is the critical point K, and condition of the water vapor in a particular sample of air, that is given by this particular point. Now, this is P is equal to constant. This is a constant pressure line. Okay. Now, keeping the pressure same, if we cool the sample, then we are following this path. If we come to this point, then what will happen? Then we will have saturated vapor, and after this point we will enter the two phase zone. So, here we are having superheated vapor and we are cooling it along this constant pressure path. So, here we will come to the saturated vapor line. So, now it is saturated, and after this even small amount of heat rejection or heat extraction from the sample, then we will have condensation. So, here we will have formation of water droplet or dew. So, this temperature is called dew point temperature.
let us denote it by D. So, this is the dew point temperature. So, you can see that for a particular sample, the particular sample means it will be at a particular temperature and at a particular pressure. It will have a dew point temperature. If keeping the pressure same, if we want to, if we start on extracting heat from the sample, then at one temperature its temperature is falling, at one temperature it will start, condensation will start in the sample, and that temperature is known as dew point temperature. So, this is our dew point temperature. Now, then we like to, let us call it dew point temperature. Now, next we like to see degree of saturation. Degree of saturation. So, degree of saturation, it is like this. Again, let us try to understand the process with the help of this TS diagram. All right. So, this is a constant pressure line and the condition of the water vapor is somewhere here. This is the condition of water vapor. All right. Now, at this condition it is having a humidity ratio is equal to W. So, for this what relationship we have got? W is equal to .622 PV by P minus PV. All right. And this pressure of course is PV. This pressure, the pressure which I have shown here, this is of course PV. Then I can come to the saturated condition. One way I have shown that I have come this way. That means, keeping the pressure constant, I have lowered the temperature. But I can come to the saturated condition by this path also. Let us say this point I denote as 1 and this point is 2. So, I can come to point 2, which is a saturated condition, by this path also. What I have done here? I have kept the temperature constant, but there is variation of pressure. So, I can come by this path also. Well, so, in that case we will have another value of humidity ratio, and as it is in the saturated condition we can call it WS, and WS will be 0.622 PS P minus PS. Okay. Now, the degree of saturation we will define as mu. We will define as mu, that is nothing but W by Ws. All right. And then we can get this relationship PV by PS within bracket 1 minus Ps by P divided by 1 minus Pv by P. So, this will be the degree of saturation. All right. All right. Once we have learnt what is degree of saturation, then we can go to another quantity which is very important, that is known as relative humidity. Relative humidity. So, relative humidity, it is expressed either as RH or phi. It is denoted either by RH or by phi. So, relative humidity, it is defined like this: phi, it is equal to mV by mVs. What does it mean? mV is the amount of water vapor actually present in the sample at a particular pressure and temperature. We have taken a sample, that sample has got some pressure and temperature. So, at that pressure and temperature, we have got mV amount of water vapor present in 1 kg in the sample, that means with 1 kg of air. So, that will give you of course W. Then if we want to make at that particular pressure and temperature, if we want to make that sample saturated, let us say we need mVs amount of water vapor. Then the ratio between mV and mVs, that gives you the relative humidity. All right. So, it is very simple, we can express it PV V by RT and PVS V by RT, or simply it is PS V by RT, and then phi is equal to, ultimately if we do the simplifications, we can have it is VV by Vs. This we can have, this is, we can have phi is equal to Vs by Vv, or we can have Pv by Ps. All right. And you can see that it is given by either the ratio of partial pressure or the ratio of the specific volume. All right. And as it is a ratio of two similar quantities, so it will not have any unit, and sometimes or most of the times it is expressed as percentage. So, when the sample is such that it is already having water vapor needed for saturation, that means mV is nothing but mVs, then phi becomes 1 or the relative humidity becomes 100%. All right. Similarly, we can have other percentages of relative humidity. Now, relative humidity is a better representation of the of the condition of air as far as evaporation or condensation is concerned. All right. If the relative humidity is less, then we can assume that the sample of air has got a higher capacity or a larger capacity of absorbing water vapor or moisture. At that condition, if somebody is sweating or there is water present or water spray inside the sample, then it will readily evaporate. So, that means, if somebody, how it is important for air conditioning, if somebody is sweating, then we will see that he is from his body the sweat will evaporate very fast, he will have the feeling of comfort. All right. Whereas, if the relative humidity is high, let us say 80%, 90% like that, 95%, then if somebody is sweating, so the sweat will collect on his body as a layer and he will not have the feeling of comfort. Similarly, if we have got wet clothes, etc., so that will not dry faster in the air. So, that is why absolute humidity gives us the amount of water vapor present in the absolute quantity of water vapor present in the air. Maybe it is important for some calculation, for some analysis, but if we want to have the idea how fast will be the evaporation process. So, if we want to know that, then relative humidity is a better property to know it, and it is it is more commonly expressed as percentage. So, we will see in our weather forecast, etc., we will have moisture content expressed as relative humidity. But these three quantities, that is relative humidity, humidity ratio and the degree of saturation, they are related to each other, and I like to write down this relationship. One can have, well, relationships between omega, mu and phi. So, one can have omega is equal to 0.622 phi Ps by Pa. Similarly, one can have phi is equal to omega by 0.622 Pa by Ps. Then mu is equal to phi 1 minus Ps by P divided by 1 minus Pv by P, and phi is equal to mu 1 minus mu Ps by P. So, these are the relationships between relative humidity, degree of saturation and humidity ratio. Well, before going to some other property, I like to describe another measurable quantities. See, these quantities, this absolute humidity or humidity ratio, degree of saturation, relative humidity, they are measurable, but they cannot be measured in a very direct manner. I have just explained how one can measure omega, but directly they cannot be measured. Maybe they can be measured, some quantities can be measured, and then using some mathematical relationship we can get these quantities. But there is another quantity in case of air water vapor mixture which can be measured directly, and that is known as wet bulb temperature. This wet bulb temperature, well, there is some thermodynamic principle behind it, and well, we do not have that much time to give a very elaborate description of that thermodynamic principle and that derivation, but in a nutshell I will try to explain what is wet bulb temperature and how it is measured. Now, before describing wet bulb temperature, so let us see what is dry bulb temperature. Dry bulb temperature is the temperature which we will get if a thermometer is placed in a sample of air. So, in a sample of air, if you place the thermometer, then you will see somewhere there is the mercury level, and that gives the temperature of the sample. So, that is dry bulb temperature, or simply we can call it temperature of the sample. For wet bulb temperature, what we do, we have similar thermometer, but the bulb of this thermometer is wrapped with the help of a layer of cotton, okay, and then this cotton is kept moist with the help of pure water. Pure water means distilled water. With the help of pure water, this layer of cotton is kept wet. How it can be kept wet? This is one of the method by which it can be kept wet or kept moist. That means, with this cotton we have got certain strip which is ultimately dipped in a container which contains distilled water. So, due to capillarity, water will come up and this portion will also remain. This portion means this hatched portion will also remain wet. And then one has to ensure that across this bulb there is enough amount of air flow. So, the sample of moist air which I have taken, that should have enough relative velocity with this moist bulb of thermometer. Okay. So, that can be ensured by different means. One is that if it is in some air conditioning duct etc., or just after the dehumidifying coil, cooling coil, where the fan is blowing the air. So, we already have a very large velocity of air. So, we need not bother, we can simply hold the thermometer like this. But if it is in a stationary room like this, suppose in this room we want to find out the wet bulb temperature. Okay. So, in this room we have to create this motion. There are different methods of creating this motion. There can be a small fan which is drawing the air with enough velocity across the bulb. If that is also not there, then there are arrangement where you have to rotate the thermometer with your hand, so that you are creating a relative motion between the bulb and the air. Generally, this wet bulb thermometer, wet bulb temperature, it is a psychrometric measurement. So, that is why what is done, a dry bulb thermometer and a wet bulb thermometer, they are placed side by side, and the whole arrangement you can rotate with the help of your hand. And that piece of instrument where you have got both wet bulb temperature and dry bulb temperature and I mean arrangement for rotating it, you call it a sling psychrometer. PSLING psychrometer. We can call it a sling psychrometer. Now, the process which takes place, that is bit complex and some sort of conjugate process. What will happen in this thermometer bulb? What type of transport process will take place? Any idea?
The wet bulb temperature will drop more than the dry bulb.
No, that is there. That is ultimately we will. That's what I have drawn also.
Water will start getting evaporated.
Okay.
Fresh water.
Okay.
And we can measure the rate of evaporation of this.
No, no, no. I will come. So, water will start evaporating because we are assuming that the sample in which it is being rotated or the air which is flowing over this bulb, that is not saturated, that is unsaturated. So, if it is unsaturated, so if we see closely, this is the wet surface. Just near the wet surface, this air is also saturated with water vapor, but here the air is not saturated with water vapor. So, the molecules of the water vapor that will move from here to here. So, this is some sort of a diffusion process or mass transfer process. So, some amount of mass transfer will take place. Now, when it is transferring it, that means when liquid water is there and due to diffusion from that liquid evaporation is taking place and that is being removed to the airstream itself. So, due to evaporation it will take up certain amount of latent heat. That means its temperature will fall down, but the air which is moving will have a higher temperature. So, a heat transfer will take place also because there is a temperature gradient. There is a concentration gradient, high concentration is there on the body of the wick. This is called wick, W-I-C-K-A, W-I-C-K, wick, wet wick. Okay. So, we have got a high concentration of mass on the body of the wick, low concentration of mass in the air. So, mass transfer will take place from the body of the wick to the air stream, but we have got a high temperature in the air and low temperature on the body of the wick because some certain amount of latent heat has been taken. So, a heat transfer will take from air to wick, all right, and this process will continue till equilibrium is reached. Equilibrium of course will reach very fast, okay. Equilibrium will reach, and then the temperature indicated by the thermometer will be the temperature required for the equilibrium, okay. The temperature that will be required for the equilibrium, and here of course one can assume that radiative heat transfer etc. are negligibly small. So, for air water system one can show that this temperature is equal to adiabatic saturation temperature. This wet bulb temperature is equal to adiabatic saturation temperature. So, we can call it dBT, we can call it WBT. Actually, one can derive it, what is the process involved, and then some sort of heat transfer and mass transfer equations are also needed, but so far we have not done those things, and I think that much details is not needed for this course. So, for air water system we will see that when this equilibrium reaches, then the temperature denoted by the wet bulb thermometer is the adiabatic saturation temperature, and it is also known as the wet bulb temperature. So, I am writing these two keyword wet bulb temperature, adiabatic saturation temperature. Okay. And here we will see that if the sample is not saturated, obviously wet bulb temperature will be different from dry bulb temperature, and wet bulb temperature will be lower than the dry bulb temperature. This is known as wet bulb depression. Wet bulb depression. All right. So, knowing the dry bulb temperature and wet bulb temperature, we will see we can determine the other properties of the moist air, and that can be done readily with the help of a psychrometric chart. Okay. So, now itself I can introduce the psychrometric chart and then of course, in some of the tutorial classes we will see how to read the chart, but now itself I can introduce the psychrometric chart. Well, so far I think whatever I have told those are clear. That means, what I have introduced? I have introduced these quantities. First I have introduced the humidity ratio or specific humidity, dew point temperature, degree of saturation, relative humidity, which is very important, and then we have come to wet bulb temperature. I have told whatever quantities I have introduced earlier, those can be measured, but not very conveniently we can measure them in a direct manner, but wet bulb temperature we can measure in a direct manner, and we will see that if we use wet bulb temperature and dry bulb temperature, both of which can be measured directly, with the help of psychrometric chart we can get the other properties very easily. And also we will see that our different air conditioning processes and calculations that can be done with the help of our psychrometric chart quite easily. Now, so now I will introduce psychrometric chart. Now, you see, psychrometry is the property of moist air, all right. And as I have described it, we can, as I have described it, we are taking this moist air as mixture of two ideal gases. One is dry air and one is water vapor. We are taking it as mixture of two ideal gases. Now, we know for any pure substance, if it is a single component substance, so this is a two component mixture. Now, if it is a single component substance, then if we know two independent thermodynamic property, then any third property can be determined. Knowing two independent thermodynamic properties, any third property can be determined. So, here what we get? Here we are getting two components. So, here 3 properties should be known, then only the fourth property can be determined. Actually, it comes from thermodynamics and Gibbs phase rule, which is not within the scope of the present course, but as we can draw some sort of analogy, we can tell it that for any pure substance, if it is single component pure substance, then what we have to know two independent thermodynamic properties to know any other thermodynamic properties. But as in the present case, it is mixture of two components, two gaseous components. So, we need to know 3 properties to know any third property. So, what does it mean that the any property chart we should have a 3-dimensional figure, because 3 things should change independently, then we will get the fourth one. Okay. But what is done, psychrometric, particularly for air conditioning and some such application, we need it at a pressure near atmospheric pressure. So, for our practical use, we can freeze one property. That means, we will make the chart at atmospheric pressure. So, pressure we make it constant. Then if one property is fixed, we now need 2 properties to get any other property, and now we can express the chart on a 2-dimensional plane. So, that is what is done in a psychrometric chart. We will have a chart which is represented on a piece of paper, that means it is a 2-dimensional plot, and in that pressure is kept constant, that is we are having the chart at atmospheric pressure. Now, if we have to do for other places like at some elevation where the pressure is lower, we need to have corrections or we need to have separate psychrometric chart. All right. So, the psychrometric chart that has a typical look. This is how the psychrometric chart looks. This is how it looks. In this direction, we have got T in degree centigrade. This is dBT or dry bulb temperature. And in this direction, we have got omega, that is kg per kg of dry air. Let us say we have got some sample somewhere here. This is sample of moist air. So, how we will get different information? This line is called saturation line. This is 100% relative humidity. This is 100% relative humidity, saturation line or 100% relative humidity. So, okay, we can use some other color. So, from the sample, if we draw a straight line which is parallel to the dBT axis, we will reach the saturation line, and this point is known as dP or dPT. This point is known as dP or dPT, dew point. If we drop one vertical line from the sample, it will cut the dBT axis and will give the dBT. So, this will give the dry bulb temperature. All right. Now, if we draw another horizontal line from the sample, and if we go to the w axis or omega axis, it will give you the specific humidity or humidity ratio. All right. And there are lines which are curved lines. There can be infinite number of lines like this. So, these are constant RH lines, constant relative humidity lines. All right. Then there are number of lines which are slant straight lines, but neither horizontal nor vertical. These are constant WBT lines. These are constant wet bulb temperature lines. All right. Then in some psychrometric chart, you will find some lines whose slopes are less than the constant wet bulb temperature lines. These are constant volume lines. Okay. So, one can get constant volume lines. All right. So, as I have told earlier that for determining psychrometric properties, any psychrometric properties, we need to know two independent properties, and using this psychrometric chart we can do the needful. I mean, we can determine any other property. So, basically one needs to know the dry bulb temperature and the wet bulb temperature. Both of them are measurable quantities. So, you know the dry bulb temperature. So, dry bulb temperature is known. You know your sample will lie on this straight line. Then you know the wet bulb temperature. So, you have to find out which is the wet bulb temperature, which is the wet bulb temperature crossing this straight line. So, knowing the wet bulb temperature means it will cross somewhere here. So, this is the point where your sample will lie. Once you know this, you can determine what is the relative humidity, what is the dew point temperature, what is the specific humidity or humidity ratio, what is the volume. So, all these things you can determine. All right. So, as an engineer, generally we measure these two quantities with the help of a sling psychrometer, and after knowing this we use the psychrometric chart to get all the other properties. There is another property, enthalpy. We will come into that property slightly later on, but you see, important thing is this is saturation line. On this saturation line, if your sample lies, then you will find you will have identical value of dry bulb temperature, wet bulb temperature and dew point temperature. If your relative humidity is equal to 100%, then you will have same dry bulb temperature, means identical values of dry bulb temperature, wet bulb temperature and dew point temperature. All right. So, that is what we can get from the psychrometric chart. Let us say this is the psychrometric chart, this is T, this is omega. So, this is the sample at state 1, this is the sample at state 2. Okay. Let us say there is a change from state 1 to state 2. So, we can have all the required quantities, means how the dew point temperature has changed from state 1 to state 2, we can find out. We can find out how the wet bulb temperature has changed from state 1 to state 2. If we are interested in this, we can find out how the humidity ratio has changed from state 1 to state 2, that we can find out. Okay. All right. Then there are certain interesting things. Let us say our state 1, okay, let us take our state 1 is somewhere here, this is our state 1. State 2 is somewhere here, this is our state 2. So, this is state 1 and this is state 2. So, what we can see that well, something like that. Well, it is something like that, that part of the process is outside this saturation line. So, obviously, there will be certain amount of condensation and heat transfer is there, definitely there is change in temperature, certain amount of condensation, and depending on the situation, what will happen if these particles are small, then they may get suspended in the air and they may create a situation like fog kind of a thing that they may create. Okay. So, seeing this thing, one can say that obviously here and here the moisture content has reduced to a great extent. Another thing you can see that is very interesting, let us take the previous example. Well, no, let me draw another figure. This is our psychrometric chart. These are constant humidity lines, constant relative humidity lines, sorry. Well, let us say we are having two different points like this. Okay. So, here you see, let us say this is O1 and let us say this is 2, and here this is omega 1 and this is omega 2, all right, and this is RH 2, this is RH 1. What I mean to say that you can get omega 1 is greater than omega 2, much greater than omega 2, but RH 1 is less than RH 2. RH 1 is less than RH 2. All right. So, you see the tendency for evaporation or tendency for transformation into water vapor, that will be higher. Where it will be higher? Where your relative humidity is
Less moisture content.
yeah, not less moisture content. Moisture content is higher here, but even then relative humidity is could be lower. With a higher moisture content, even with a higher moisture content, the relative humidity could be lower, because it depends also on temperature. Okay. And whereas here the moisture content is much lower, but the relative humidity could be much higher. Okay. So, that is how the psychrometric chart gives us lot of information, and these informations we will see how we can utilize for our basic calculation of the air conditioning processes. All right. So, if we quickly like to recapitulate, on a psychrometric chart we will have two axes. One axis, this is dry bulb temperature, and this one is humidity ratio or specific humidity. Apart from these two, the important points which we will have on the psychrometric chart are this wet bulb temperature line and relative humidity line. From any point, if we draw a horizontal line and if we go to the saturation line, that is 100% relative humidity line, then we will get the dew point temperature. Okay. And and if our point or sample is on the 100% relative humidity line, then we will have identical values of dew point temperature, dry bulb temperature and wet bulb temperature. So, that means these wet bulb temperatures, they are also, let us say WBT, but they are also in degree C. These are also in degree C. These are in percentage. This is percentage 100%, this is also in percentage. These lines are in percentage. These lines are in degree C, and of course, this axis is degree C and this is kg per kg of dry air. Now, if you see the psychrometric chart in any book, whatever I have discussed, that will be clear. So, we like to make a break here, and next day we will start the enthalpy of moist air, how to calculate the enthalpy of moist air. Thank you.